Hey, I'm Todd Sharp, and thanks for joining me for this session today at Oracle Database World. This is going to be a very different type of session, and I really hope that you enjoy it. Today, I'm going to talk to you about how I uploaded my brain to the cloud, that's right, so that I could examine the relationship between my brain activity and my video game performance. Now, since this is Database World, we'll focus on the SQL bits of the project, but if you're interested in learning more, there will be plenty of links where you can watch other videos and read more about it. I am a developer advocate on the database team here at Oracle, and I spend my time creating tons of digital content for developers and just, talking to developers, learning about what they're using, learning about how they're using it. I then take that feedback to our product teams, and I help use that feedback to help make our products and services better. If you'd like to connect with me or check out some of my content, here is my Twitter handle, YouTube channel, all those links, and I would really love to connect with you. So let's get right into it. A few months back, I read a really excellent but kind of old blog post that explained how to hack a toy called a MindFlex to extract and analyze the EEG data within it. Now, at first, I couldn't believe that such a thing existed. I mean, sure, gimmicky toys have been around for ages, so I wasn't really shocked that a toy claimed to read your mind. It's not really uncommon to fake this kind of gimmick. But the MindFlex contains a real, legit EEG chip that actually does read your mind. And to me, that, seemed almost too good to be true. So I wondered if it was possible to take this hack a step beyond just reading my brainwaves. Instead of just reading the data or, using the data to control something else, what if I were to read the data while doing some kind of task and see what the data reveals about my performance during the task? Now, obviously, I'd need to do something with quantifiable data in order to properly compare the brain activity to the task results so that I could find out if my attention levels correlated to that task's success or failure. So, what task to perform was the next question. Now, around this time, I had also been thinking about how to integrate some of my video game statistics into a project. So, it was this light bulb moment, and I kind of figured that this combination would be a fun one to play around with. So I asked myself, if I could hack the MindFlex and wear it while playing video games, Call of Duty, what would that data show? Could I establish a relationship between brain activity and video game performance? In other words, when I'm really focused and attentive, do I play better? When I'm distracted, do I play worse? These kinds of questions. Is there no connection at all? I really wasn't sure if these tests would succeed, but I decided to find out. So once I established the idea for the project, I started asking myself some questions. The first question was, can I read my own brain data? And if so, is the data valid? Next, I asked myself, can I improve my performance in video games by being super focused and concentrating? Now, to answer those questions, I decided to establish a few objectives for the project. The first objective was to capture my brain data at home in an accurate and cost-effective manner. The next objective was to capture my brain data while playing a video game, and then somehow quantify my game performance via data. The final goal was to establish and visualize a relationship between the brain activity and my game performance. Once these questions were asked and the objectives were established, it was time to come up with the architecture for the project. Now, here's a basic overview of the architecture that I came up with. My brain activity would be captured by an Arduino connected to the MindFlex and published to an MQTT topic in the cloud. A Micronaut Java application would consume that topic and then persist that data into my autonomous database instance. My game stats would be obtained via scheduled calls to the Call of Duty API, which returns match information as a JSON object. The game stats would also be persisted to the database, obviously. Now, once I had the data, the next step would be to query the data and analyze it. And that's what we're going to focus on in this session. Now, as that last slide illustrated, there are a lot of technical bits involved in this project. From the MindFlex itself, which was hacked with the Arduino board so that it could upload my brain data to the cloud, to the Java application that consumes it and renders the front end, we're talking about C++ code, Java code, HTML, JavaScript, and CSS. But the part that you're probably most interested in is the SQL code. So let's dig into that and see how I store and query the data for this project. So the first challenge was how to deal with that JSON data, as you see here on this slide, that was returned from the Call of Duty API. Now, clearly this can be tricky because I don't have control over the format of that JSON. So if I were to create like a normal traditional type table with columns for all the values, I'd potentially have to change that schema every time the JSON data changes. But Autonomous DB gives me a great solution. Store the data as JSON. This lets me remain flexible, but still gives me the ability to query and aggregate however I want. Now, as I said, this here is an example of the current format of the JSON data that comes from the API. And here's how my game table works. It's a very basic table. Just an ID column, a created on timestamp, and the match column, which stores the JSON data as a clob. So if I query this table, you can see that the JSON data is stored in its raw format, essentially just a large JSON string of data. There's no need for me to worry about the keys or the values or the data type even of the data stored in that JSON string. It can be whatever, and it can even change from one row to another. I don't have to update the columns in the table if the JSON changes. I just store the raw value. Now you might think that this table design would make accessing the data in the match column difficult, but as you'll see on the next slide, it's actually quite the opposite. So in order to query the match data, I simply reference the JSON column with dot notation, as you see here. It doesn't matter how deeply nested the value is, and as you can see here, I can access any value inside that JSON without trouble. This gives me a more normalized view of the match data, and this is the first step in analyzing that match data. Now, this match data forms the basis for many of the aggregate queries in the application. So having that normalized view of that data was extremely important to me. Instead of referencing each value with dot notation in all of my queries, I figured it would make more sense to create a materialized view of the game data that refreshes on commit to the game table. This way, I'd always have the match data in rows and columns for joining, grouping, and aggregating the data. Now, the fact that the data behind the materialized view is stored as JSON is really unimportant. My queries have no need to even consider what the underlying data is. They just select the value from the view as if it were stored in a traditional table. And if the JSON data is missing a particular value for some reason, or the JSON schema changes, the materialized view will return a null value instead of throwing an exception. How can you not love that? So the materialized view properly infers the column data type. So aggregations such as the one shown here work as expected. And they're much easier than referencing the JSON value with dot notation. My queries are just easier to write and easier to read. So my brain data is stored in a table that holds the individual values from the MindFlex readings. Since I was in control over that format, I was the one producing it, there was no need to store it as JSON. The MindFlex data was sampled every 5 seconds and contains the individual brainwave readings as well as values for attention and meditation that are calculated using a proprietary algorithm on the MindFlex EEG chip. Attention and meditation form the basis of many of my reports in the project, since they're, friendlier type data than the raw brainwave data. The average delta and theta, for example, don't really provide much meaning to me, but attention and meditation on a scale of 0 to 100, those mean a lot to me. So once I had both the game and the brain data, I combined them with a query that joins the brain data to the match data based on the start and end timestamps of each. Now, this is the basis of how I examined the relationship between the data by looking at metrics like game score and accuracy compared to my average attention and meditation, among other factors. So you're probably thinking that joining on timestamps isn't the most efficient or performant thing in the world. And you're right. But thankfully, there was no real need to have this data be real-time data. So I turned it into a materialized view that automatically refreshes itself every hour. Now, this frequency worked out just fine for me because the game data from the Call of Duty API is also retrieved once an hour. So there's really no need for a more frequent refresh of the materialized view. Now, of course, this also gives me the added bonus of having another nice normalized view of the combined data that I could use for further reporting queries. Now, as I wrote various reports for my front-end tables and visualizations, I started to notice that certain queries were pretty much identical, maybe with the exception of a grouping column. Now, of course, at first this wasn't a big deal. I would just update multiple queries, not a big deal. But as I added more dimensions and more values to the reports, I started to get a little bit annoyed at updating all of the separate reports, and I decided to address the situation. So take this query, for example, as you see on this slide. This query groups my game stats by the attention range. Now, compare that to this query, which groups my game stats by meditation range. As you can see here, other than the grouping, the queries are identical. Now, wouldn't it be much nicer to combine the queries, but somehow change that grouping based on a parameter? Now, in the old days, this would be tricky, or even impossible. But thanks to SQL macros, it's now really easy to accomplish. Let's see how to do that. So as you can see, the macro definition shown on this slide contains a factor argument that is passed in. The query that is executed looks at that factor and simply changes the grouping accordingly. Now I have one query that lets me group by attention or meditation just by passing in the desired factor. Now this is much more manageable, but it's still efficient and still performant. So let's switch gears now to take a look at how the Java application connects to the database and handles persistence and querying the autonomous database. So once my queries and views were created, the next step was to create and wire up the Java application with Micronaut. So the first step here was to configure a database connection, which is made easy by Micronaut support for auto download of my autonomous database wallet. I just had to configure the data source with my credentials, as you see here. And in addition to those credentials, I just needed to set the database OSID, and this gives Micronaut all the information that it needs to download my wallet and configure a secure connection to the data source. Next, I created Java entities that map to the database tables. Each property in the entity maps to a column in the table. Micronaut uses the naming convention of the class as well as the properties to map the object to the table. For data access, repositories were created that extend the built-in Micronaut interfaces. The entity on the previous slide and the repository shown here are all that Micronaut needs to create the plumbing for basic CRUD operations for the entities. And all of the heavy lifting of introspecting and constructing the queries happens at compile time. So runtime performance is vastly improved. So in addition to the basic CRUD support that Micronaut supplies, I also added some native queries via an @query annotation so that I could retrieve the data from my SQL macros and views, as you can see here on this slide. So over the course of a month, I spent over 20 hours playing more than 150 online multiplayer matches and collected over 12,000 records of brain data. So the big question is, what does the data show me? Let's dive into the results and see how my brain activity relates to my game performance. Now, originally, when I established my hypothesis, I figured that there would be like a really direct linear correlation between my attention levels and video game performance, as illustrated on this slide. Of course, the more I pay attention, the better I will score, right? I mean, that seemed to be a valid assumption. As I said, this is what I assumed the data would look like. But in reality, my game stats start low when my attention is low and steadily increase, but they peak in the 41 to 50% range, and then they start to decline. Now, this was really interesting to me because I hypothesized that there would be that corresponding increase in performance and attention. So this data seems to disprove my hypothesis. But, in hindsight, this actually makes sense. I mean, video games require attention and focus, but paying too much attention can be detrimental. Ask any gamer about what's going on in their brain when they have like a really good match, and they'll tell you that they're like locked in mentally, but you're not really like hyper visually focused. Instead, you tend to almost like zone out and let your eyes and your ears and your brain just observe the entire picture. Instead of like visually scanning the screen and like looking for enemies, you tend to do best when you place your visual focus on your crosshairs and just observe and listen for footsteps. You almost have to like intentionally not focus on every little detail happening on the screen and just let your brain react to the minor changes in the environment on the screen and, react to that visual or the auditory stimuli. If you like explicitly try to aim and shoot in a video game, you're often going to miss the target. You tend to play best when you're reactive instead of proactive. Now, my score per minute value follows this trend, with that low score per minute for low attention ranges, rising to that peak at 41 to 50%, and then falling with increased attention. Accuracy follows the same trend as the previous metrics, essentially proving that I play my best when my attention is in that 41 to 50% range. Now, interestingly, the meditation data shows a decline in performance when my meditation value, or calmness, increases. So what this means is I do better when I'm not calm. This was a little unexpected, but it actually makes sense when I think about it. I mean, obviously being calm or relaxed would indicate a decrease in reaction time, and slower reflexes mean that I die faster, I die more often, and I just score worse. All of the other metrics that I tracked show the same trend for meditation data. When I'm more calm, I play worse. So, is there a direct, measurable relationship between superior gaming performance and high levels of attention? Or are there just too many factors at play? Well, as you've seen here, there certainly seems to be trends in the data that indicate my performance does relate to my brain activity. My performance is best when my attention and meditation values are moderate. When I pay too much attention or I'm too calm, my performance decreases. So I hope that you've enjoyed this session and maybe you've learned something new about Autonomous Database in the process. If you'd like to learn more, please check out my project page or the blog post listed here. And if you'd like to connect with me, please check out my blog or hook up with me on Twitter or LinkedIn or any of the socials out there. And thanks for joining me today. I would be happy to answer any questions that you may have.